Hello everyone, I will be solving problem 2.33 from Introduction to Electrodynamics by Griffiths. The problem states, consider an infinite chain of point charges, plus and minus q with alternating signs, strung out along the x-axis, each a distance a from its nearest neighbors. Find the work per particle required to assemble this system. We're given the partial answer, which is negative alpha q squared over 4 pi epsilon naught a. And our problem is to determine what that constant is, the alpha constant, which is also known as the Madelung constant. So to start off this problem, we can start by drawing what this chain of charges looks like. So let's assume we start with a positive charge over here, and then a distance a away would be a negative charge, and so on and so forth. Oh, a negative charge. Okay, and so because we need the work per particle, we can just start off by adding a particle to this system that we have drawn right here. And let's say I wanted to add a particle to the left, meaning it's a negative charge. Okay, and we know that the work to bring in one particle is 1/2 QV. So we need the potential and the charge, and we can find both easily. So the charge is negative, and then the potential. So the first potential would be for the charge that's right here, the first positive one, and that would look, would just be A, and then the charge that we're multiplying by, which is Q. But we also had to take into consideration the other charges, right? So now we move on to the first negative charge, and we basically have almost the same term. The only difference is the distance. So we can see it is 2 A's away. And I did add this negative because it's a negative charge. And we repeat the same thinking for the second positive charge. And this time it's 3 A's away. And lastly, kind of, because this keeps going, but in our example, we would basically have negative Q over 4 pi epsilon naught, and the distance is 4A. And like I said, this will keep going. Alright, so when we look at this, not only we can take out a constant from all these terms, which is Q over 4 pi epsilon naught A, but we also have to notice that we are focusing on the work that it takes to bring this one charge, and we're only considering the potentials from the right side of the charge that we're bringing in. But we have to remember that this is an infinite chain. Therefore, we'll have multiple charges literally looking the same way, but to the left. And these are also distances A away from each other. So basically, the point is that the work that I have written down right here would have to be multiplied by 2 to take into consideration that we have charges to the left and to the right of the charge that we're bringing in. So this would basically end up looking like this. So the 2 would cancel out, right? The 1/2 would cancel out by multiplying it by 2. And we would have negative q times q over 4 pi epsilon naught a. And then we would have, well, that is literally the first term, so that's a 1. And then next, only the 2 remains on the denominator, so we have 1/2, and then 1/3, 1/4. And, well, actually, this is what our constant would look like. This is the Madelung constant. So this condenses to the work being negative alpha q squared 4 pi epsilon naught a. Okay, but now we have to actually determine what the constant is. To do this, we can look at the Taylor expansion of natural log of 1 plus x. And this one looks like this. And it's very similar to what we have. So in order to have our Madelung constant look like this expansion, we can make x equal to 1. So if x equals to 1, this whole thing will look like this. So natural log of 1 plus 1, and we would have 1 minus 1/2 times 1 plus 1/3 times 1 minus 1/4 times 1. Therefore, our Madelung constant is just the natural log of 2. So if we want to plug in into the work that we found, we basically would have that the work is equal to a negative natural log of 2 times q squared over 4 pi epsilon naught a. Okay, so we successfully calculated the work per particle to assemble the system, and we defined the Madelung constant. Thank you for watching.